All right, guys, welcome to 7.6 Growth and Decay Functions. So, last time, and this says 7.6, but really in your books, I want to make sure of something here. This is 7.7 to be clear. We're going to be writing exponential functions, but we're going to focus on these growth and decay functions. Okay, so the true title is Writing Exponential Functions. Writing exponential functions is what we're doing today. We're going to kind of skip the first part of the lesson, and I just really want you to focus on two equations for today. And I want you to memorize them because they're very important. As we've talked about before, this is how our money grows when we have compounding interest in an account. So it's an important equation to know, and I actually want you to memorize this equation for the test. So I would really want you to memorize this equation, which basically just says that the final amount of some investment, y, is equal to the initial amount, which we call the principal, A, okay, multiplied by 1 plus R. R is the rate as a decimal. So if I say like 5%, R then would be equal to 0.05. You have to write the percentage as a decimal by moving the decimal 2 places to the left. Okay, so just don't forget that. And then T is always going to be time. Typically time is in years, but it depends on what we're talking about. So that's the equation for exponential growth. Let's get right into using some of this. Now this one is not in the notes that I've provided for you, but it's a good one. So I just want to show you guys how this works, and then we'll do one that is in your notes. So the prize for a radio station contest begins with a $100 gift card. So you get $100 if you win on day one. Once a day, the name is announced. The person has 15 minutes to call, or the prize increases by 2.5% for the next day. Okay, so it says write an equation to represent the amount of the gift card in dollars after T days with no winners. Okay, so for this one, what we're going to do is we're going to set it up using our exponential growth function. We know that we don't know what the final amount is, so we're going to keep y as is. But we do know what the initial amount is, the a value, that's 100. And then we know that the R value is 2.5%. So I'm going to write that as a decimal, 0.025. All right, that's 2.5%. And then that's all taken to the T, where T is in days. Okay, so we don't know what the time frame is, but every day is when this happens. Okay, so that's my equation for this thing. Now, once I know that equation, which that's the equation piece, what this is asking me to do for part 2 is it's asking me to find out what this thing is worth after 10 days. So after 10 days, I'm going to just plug in a 10 for time. Okay, so y then is equal to 100 times 1.025. I just added the 1 plus the 0.025, all to the 10th power. Now be very careful here, you guys, okay? And actually I'm going to slow it down because some people make this mistake way too often. Remember PEMDAS, okay? Remember that we always do our exponents first. So where you're going to start this in your calculator is you're not going to start with the 100. You're going to start right here. You're going to punch in 1.025. You're going to take that to the 10th power, which I encourage you to do right now with the video. Make sure that you get this answer correct. Then you're going to multiply that answer by 100. Okay, when you do that, you get y is equal to $128.01. Okay, so if you win the prize on day 10, you get $128.01 on the gift card. Okay, now it's your turn. This is a very similar problem. Okay, we have a college tuition that's rising 5% each year since 2000. If the tuition in 2000 was $10,850, write an equation for the amount it will be T years after 2000, and then predict what happens in 2015. Okay, so this is an exponential growth problem. So we have y is equal to the original amount. The original amount is 10,850. Multiplied by 1 plus the rate, 0.05. Okay, 5% is a decimal. And then all to the t. So they want the equation in terms of t. That's part A. And then for part B, we have predicting the cost in 2015. Okay, so in 2015, we would have y is equal to 10,850 times 1.05 to the 15th power. And if we do that out, you take 1.05 to the 15th on your calculator, multiply it by the 10,850. What you should be getting is $22,556.37. Okay, so yes, that's actually pretty accurate, especially if you're looking at some place like PUC, where now we're paying, what, $30,000 a year or something like that in 2021. So, but I think with coronavirus this year that I'm making this video, I think that the tuition may have dropped. But anyway, that's a side conversation. So the next one that I want you to know, okay, there's only 3 equations. This one's essentially the same. This is the same exact equation, you guys, for compound interest. The only thing that differs here with this one is that if it's compounding more than once in a time frame. Okay, so we know that sometimes interest compounds monthly, but our time might be in years or something like that. So everything is the same. Okay, the letters changed a little bit. We said now that A is the current amount, is equal to the principal. Okay, that's the original amount that we put in. So P is the original amount we put in, times 1 plus R. R is the rate as a decimal. Over N. N is the number of times that the interest is compounded each year. All to the nt power, so n times t power. So the first thing we're going to evaluate when we do these, if you use compound interest formula, is we're going to evaluate this thing. So that you only need to use this if something is compounding more than once in a year. Okay, if it's only once a year, you can use this guy, the equation for exponential growth. But if it compounds more than once a year, you have to include this n value. That's the only thing that's different. Okay, so you just got to kind of remember that, keep that straight. So here's another example that is not in your notes, but pay attention to this. So parents invested $14,000, 6% a year, compounded monthly. How much will there be in the account after 10 years? Okay, so the principal is $14,000. The interest rate is 0.06. The time frame is 10. And then n, since it's monthly, you have to figure out how many months are in a year, and the answer to that is 12. Once you know the PNRT, you plug it into your compound interest equation. So A is equal to 14,000 times, this is wrong. This should be 1 plus. I don't know why that's in there. Okay, 1 plus 0.06 divided by n, which is 12 in this case, all to the nt. So that would be 12 times 10. So the first thing I have students do is to calculate this part out. 12 times 10 is 120. Okay, then I have them calculate this out. Okay, so if you calculated that piece out there, that comes out to 0.005, I believe. So the next step here is going to be to rewrite this. Okay, 1 plus 0, so you take 0.06 divided by 12, add it to 1, you should be getting 1.005. Okay, and if I take 12 times 10, that's to the 1/20th. I encourage you to do this step. Don't try to just plug it all into your calculator. Do that step first, combine what's in the parentheses, and then multiply this out. Then once you do that, make sure that you do this first in your calculator. Take 1.005, take it to the 120th power, then multiply it by 14,000. And when you do that, what you should be getting there is $25,471.55. Okay, not bad for doing nothing, right? You let that money sit, gains interest, and then after 10 years, it's worth 25,000 bucks. So pretty cool. It's nice when you can find an interest rate that's 6%. Okay, so your turn. Determine the amount in an investment of $300 is invested. That's more like it for you. You probably could come up with $300. Invested at an interest rate of 3.5% compounded monthly for 22 years. Okay, so hopefully you can figure this out. The P here, the principal that you start with is 300. The rate is 0.035. The N value here is going to be, it's compounded monthly. So this is the N value, which is 12, and then 22 years is the time frame. So let's go ahead and plug this in. We get A is equal to 300 times 1 plus 0.035 over 12, all to the 12 times 22. Okay, so on your calculator, what you should be doing here is you should be evaluating this piece and then rewriting this. So A then is equal to 300 times, if you do 0.035 and divide that by 12, you get this really long decimal actually, which is 1.002916667. Okay, and then when you do 12 times 22, you get 264. Okay, so when I do this out, for example, for this example here, and it says example 2, but I actually think that it is example, let's see, what example is this? This might even be example 6. Let me just look at that for you guys real quick. This is example 6, yes. So example 6, so sorry we're skipping around a little bit. But to finish this out, for example 6, let's go ahead and do this. If you do this in your calculator now, we're going to do 1.002916667. Take that to the 264th power. Okay, then multiply that by 300. And you should be getting something approximately close to $647.20. Something like that. Okay, so let's keep cruising here. Now we're going to get into exponential decay. So for exponential decay, I want you to notice that it's the exact same thing. The only thing that's different in the exponential decay is this negative. Now we're subtracting the rate. We're not adding the rate to our original, so we're subtracting. Okay, so same exact deal, we're just subtracting now. So the population of Campbell County, Kentucky has been decreasing at an average rate of 0.3% per year. In 2000, the population was 88,647. Write an equation to represent the population since 2000. Okay, so they want it in terms of T. Okay, so our A value here, our original value here is 88,647. Our rate is 0, careful with this rate, you guys, 0.003. Okay, there's an extra 0 there because this is 0.3, right? So if you put this 2 places, you'd be at 0.3. So that's my rate. And then my time frame here, well, my time frame will eventually be 10. But they want our just T in terms of any, they want us to be able to use this for any year for our equation. So the first thing is, let's write our equation. Let's say y is equal to 88,647 times 1 minus 0.003, all to the T power. Okay, then on the second part of this is they want us to evaluate that when, by the way, when I take 1 and I subtract 0.003, I get 0.997. So with a decay function, this should always be less than 1. And then this will be down to the 10th power. So if I take that to the 10th power, okay, and then multiply that by 88,647, what I end up with is 86,023. And then we're not going to put 0.2, which is what it technically is, because we're talking about people, so we're just going to round down. Our population is approximately 86,023 people. And that's it, you guys. So if we have a decrease, just know that we're using the subtraction sign. So the big takeaways here are the equations. So we need to know 3 equations, but they're essentially all the same. One is for exponential growth, where we add the rate in. The other is for exponential decay, in which we subtract the rate. And then the third equation deals with compound interest. This is you only use this one when something is compounding more than one time in the time frame. So if it's like monthly or weekly or daily over a certain period of years or something like that, then I know that I'm going to have to include this in for compound interest. All right, guys, that's it.